talk a little bit about ROC curves and area under the curve. It's kind of one of my favorite topics, and also actually really important because a lot of times one of the most important things about machine learning is that you need to be able to do a good evaluation of your machine learning tool. And there are lots of different metrics. I like to use personally rocking curves, or AUC, the area under the curve, and also sensitivity and specificity. Those are kind of my go-to. And there's also others that you can use, but these are the ones I like. And so it's always good to kind of review that. And I would suggest that, and I'll put the web link here. This is actually from Google, that you actually go there and actually run this yourself so you can really do it. And then maybe even make a video yourself to see if you can teach yourself about this topic. So what are rocking curves? Rocking curves are essentially receiver operating characteristic. That's what they stand for. And this has been around a long time. It actually comes from World War II radar detection. So it's a very engineering viewpoint, and it's been around for a long time, but it's been very useful for evaluating our different machine learning models over many different thresholds. Now, the typical way you'll see one of these rocking curves is it'll be plotted with the TPR, or the total positive rate on the vertical axis and the false positive rate on the horizontal axis. Now, those of us that are more in the medical field would like to use sensitivity and specificity. So the vertical axis, the TPR, is the sensitivity, and the horizontal axis is 1 minus specificity. Now, you'd always like to have the area under the curve, the AUC, as close to 1 as possible. This is the ideal situation, which you really can't get to, but it's good to know that that's the ideal. Let's kind of move our way down to here. So this is important. The area in the curve, when it's 0.5, is basically like a coin toss. That's a terrible model. So if you do a calculation, or you're reading a paper and you see the area under the curve, the AUC is around 0.5 or 0.6, you know it's a pretty terrible model. Actually, what does it mean when it's like 0.4? Actually, this means this model is even bad. It's actually worse than worse, because it actually tells you exactly the opposite of what you want to know. So hopefully you don't have any models that have area under the curve which are less than 0.5, which essentially is anti-correlation, but are at least something in the range of 0.8 or 0.9. That's where you feel like you've gotten a little bit better model. Anything like 0.6 or 0.55, you might as well throw that model away. So here are some pictures of different models, and a little bit better intuition here. The first one has an AUC of 0.65, which is, not that great. Let's look at this one, an AUC of 0.93. This is really kind of a model you'd want to have, which is much more closer to what you'd want in a well-functioning machine learning model. So this is your sensitivity. This is your 1 minus specificity. So this is good because it tells you a little bit about the trade-offs. Now, if you have a very low specificity, you're way over here, but you have a lot of sensitivity. As you drop your sensitivity along this curve, you're going to get better and better specificity till about here, where you start to lose your sensitivity a lot. So you have to decide where you want to operate your threshold, and that's an important parameter you're going to pick in your machine learning model, is going to be your threshold. It turns out that logistic regression actually has a threshold of 0.5. It's kind of hard to find that, but that's typically where the threshold is set at. But in any case, whenever you create a model, you'll be setting the threshold, and your threshold will depend on exactly what you're doing. So here we have another picture here where we have 3 different choices for operating threshold, and that's really up to the user to decide what that's going to be, and it really depends on what you're trying to do. Sometimes you'll like to have a lot of specificity, and then you'll trade off lower sensitivity. For example, here in case A, if you're operating here, you're going to operate with a relatively high specificity on this side, but a relatively lossy sensitivity. Maybe you're around 0.6. You may say, no, I want a model I want a system which is very, very sensitive and maybe not very specific. That would be C, operating point C, where you have a threshold which is very sensitive. Maybe you have a pretty low threshold, so you're very sensitive, but you're not very specific. So, or you can run here in the average. Now, in the medical field, some of you may be used to the idea of the D-dimer for deciding whether someone has a pulmonary embolus, or doing a CT scan to see if someone has a pulmonary embolus. And this might be a little bit of a way of understanding this model. You can think of point C as being very, very sensitive, like the D-dimer. So you can get a D-dimer on a patient, and if it's positive above a certain threshold, it says that this person might have a pulmonary embolus. However, we know there's many, many causes of a high D-dimer, so there's going to be lots and lots of false positives, which is why you're way over here. And so the treatment for a PE is actually going to be anticoagulation. So just having a D-dimer that's high, you're not going to want to use that by itself. You're maybe going to get some other confirmatory study, maybe a CT scan, and that's going to have to be a lot more specific. So this needs to operate way over here. Maybe not even at A, maybe it's operating way over here, although we may actually have a different curve, which is actually probably the CT scan will be much more like this curve. So hopefully you can have your CT scan, which is read by a radiologist, to be both very, very sensitive and very, very specific. So maybe you tolerate specificities, maybe down to here, which is very, very specific. Actually, you got your sensitivity initially, so maybe you're operating around here. We're very, very sensitive. And hopefully have very good specificity and sensitivity for picking out your PEs. So this is a little bit more of, and you should play with this yourself, of what this might look like. So let's take a nice distribution which is set, and usually the threshold is 0.5. As I said, this regression, usually the threshold is set at 0.5. So if you have a data set which is very well separated, so let's say this is going to be a threshold for, let's say the D-dimer, and it's relatively separated. If the D-dimer is low, then we're going to say there's no blood clot, and if the D-dimer is high, we're going to say there might be a blood clot. Okay, so in that case, what's going on? We're operating right about here. Let's see if that's a really good place to be. You can see that your sensitivity is pretty good. Your sensitivity, which is the same as a recall, is 0.83. But, you might actually think that, hey, I'm going to be missing a lot of people that could have a PE if I do this. And that's going to be a problem if I'm missing those people. And so I really don't want to be missing all these people here and saying if the D-dimer is negative or low. So actually I might need to operate really with a much lower threshold, or as you can see with the curve here, it's going to higher sensitivity. So actually I might be way down here. Okay, so if I'm operating way down here, let's see what happens. What's going on here? Well, definitely you're not missing any people that have a PE, but you have a lot of these would be false positives. The orange would be ones that don't have a PE. The purple are the ones that have it, the squares I mean. So in which case you're going to get a lot of false positives. So we can look here in the curve here. You're operating at a very high sensitivity. Or look here. They have a positive predictive value, but what's happening here is you have 23 false positives, which is not what you want. But it's okay if you have that, because you need to have a confirmatory study. So you're getting a lot of false positives, but you're also knocking out a lot of people that don't need a CT scan to confirm they have a PE. So what if we improve the threshold and we raise the threshold to be a lot higher? And let's say this is the same distribution and it's more like maybe like a CAT scan, although not exactly. If you go to here, you're going to be very, very specific. But your sensitivity is not going to be that great, and you might be missing these people that have PEs. But the question is, are these really clinically significant PEs or not? And that's really a clinical question that you have to figure out. The main point I want to bring across is that if you play with this curve, you'll be able to play with the rocking curve, understand how there's a trade-off always between specificity and sensitivity. If you want to have something that's very, very sensitive, then it's not going to be very specific. And if you want something to be very specific, either moving down here, it's not going to be very sensitive. But the way you can get around that is by having two tests, where you have one test which is maybe very sensitive and a second test which is very specific. So I'll leave that for you to play with. Go ahead and go to the website directly. You'll learn a lot more than you will just from this video by actually playing with the thresholds in the curve and actually changing this thing around. One other thing that you can do is they allow you to take a very imbalanced data set and play with it, and also a unseparated data set, and see how that works. So play with that.